Let's move on to part 2 of chapter 5, which includes section 5.3 and section 5.4. In section 5.3, we will introduce some special condition for pertinent to the electrical and magnetic vector potentials. They are the so-called Poisson equation and Laplacian equation. And in chapter 5. In section 5.4, we will try to find the so-called unit length capacitance, unit length conductance, and unit length inductance for a particular structure, for a particular geometry. In section 5.3, we will explain the physical implication of Poisson equation, and as well as the so-called Laplacian equation, and we will look into a simple parallel plate capacitor structure to find out the charge and field distribution in this structure and derive the so-called equivalent capacitance for such kind of structure. So we already seen in section 5.2 that for the steady state case, that is, have no time variance, then the electrical field intensity can be expressed as the minus of the gradient of V. V is the electrical potential, which is conventionally referred as the voltage. And we know that in Maxwell equation, the third equation is Gauss's law of electrical field, which states that divergence of electrical flux density D equals to the charge density at your observation point. Not this is Maxwell equation in differential form. So in differential form, we are concerned of the field in a particular point. In contrary, in chapter 2, when we look into the integral form of Maxwell equation, we are interested in the relationship between the field and the charge occurrence in a region. And usually the differential form of Maxwell equation are more convenient to use because they specify the source and field relationship on a particular point. All right, so compare equation 5.48 and 5.49. We can substitute the electrical flux density D with the minus of the gradient of V times permittivity epsilon. And it still equals to the charge density rho. Okay, so we got equation 5.50. So this is the charge density equals to the divergence of the gradient of electrical voltage V. And here we will, so this is the equation we just derived in the previous slide. We attempt to use the vector identity here, okay? So we know that the divergence of scalar times a vector, that is phi times A, equals to phi times the divergence of A plus the dot product of A and gradient of phi. So you need to compare the two equations to identify that the phi in the top equation is actually the permittivity epsilon. the A vector on top is actually the divergence of, not divergence, sorry, the gradient of V. So you substitute phi with epsilon and substitute A, the vector A, with gradient of V, you end up with this equation over here. And note that the second term of the left-hand side is the dot product of the gradient of epsilon, the gradient of permittivity, and the gradient of voltage V. And if the environment is a homogeneous material, is a isotropic material, 均匀的材料，所以它的那个 permittivity epsilon 不随位置而变化，是一个定值，是一个 constant. So if this is a isotropic material, homogeneous material, then the gradient of permittivity epsilon must go to 0. Then equation 5.52 can be simplified as this. So for any point in the space, if the voltage at that point, the Laplacian of the voltage at that point is non-zero, then it must comes with electrical charge density, electrical charge density. On the other hand, if there is no charge on that point, then the Laplacian of the voltage at that point is 0. Be careful about this. I'm not saying that if there is a voltage, if there is an electrical charge, then you must have. 注意到哈，我这边讲的要厘清的事情是，有电荷会在空间中建立不均匀的电压分布，所以不是电压等于0就叫没有电荷啊，电压不等于0就叫有电荷，不是这样哦，所以要小心的地方。这边假如有电荷的话，那个位置有电荷的话，它的电压的 gradient， 不对，对不起，讲错了，它的电压的 Laplacian 不等于0，搞不好那一点电压刚好等于0啊，但是它只要旁边的电压的空间分布，是有变动的，那它有可能 Laplacian 不等于0，那个地方还是有电荷的，所以反过来，空间中，这个地方有电荷啊，这边就有电场，这边就有电压，所以这个地方有电压，但不代表这边有电荷。你要看的是这个电压的上下左右前后都稍微移动一下看，找出它的 Laplacian。它的假如这边没有电荷的话，这个 Laplacian 会等于0。好，这个要小心的啊。So this equation, that is the relationship of the distribution of charge density and the non-zero Laplacian, is referred as Poisson equation. 我小时候第一次看到这个的时候，以为是 Poisson equation， 然后高中的时候有一个老师有一个补教老师OK 好，天哪，我高中就上补习班了，比那个高小姐还糟糕真糟糕。他是那种 Poisson equation 后来到大学自己在看法文书，在说根本不是要念 Poisson， 这个念 Poisson 因为法文的 OI 是音标的那个 WO 吧Poisson， 那意思是有没有人会法文的？好像是 fish 的意思，对不对？OK 好，我回去查一下刚学你还好意思举手 OK。 哦，好，我忘记是 fish 还是海鲜，应该是 fish 的意思。OK， 好啦，刚好只是一个人的姓氏而已。好 ，So the Laplacian of the electrical potential is the negative of the electrical charge density at that point. Be careful, at that point, divided by the permittivity epsilon. So the Poisson equation governs the relationship between the volume charge density low in a region of uniform permittivity epsilon to the electrical scalar potential V in that region. So you have the relationship between the permittivity, charge density, and electrical potential. So actually this relationship can be seen from this equation. This is what we have in section 5.1 when we try to express the relationship of source and potential. So electrical charge should be related to electrical scalar potential as a second-order differential equation. And the so-called second-order differential equation of wave equation involves both spatial distribution, the variation in spatial distribution, 空间的 spatial 不是特别的 spatial 是那个 SPAITAL TIAL 空间上面的分布 spatial distribution of the electrical scalar potential as well as the time variation. So you involve both time and spatial variation. However, in the case of the static field, in the static field case, you don't have any time variation. So the second term goes away, and you happens to have the Poisson equation, the Laplacian of the electrical potential equals to the minus of rho over epsilon. In Cartesian coordinate system, the derivation for having the Laplacian of the electrical potential is relatively simple. Just follow equation 5.54 and perform second-order derivative of potential V with respect to x, y, and z, respectively. And for the one-dimensional case, okay, for the one-dimensional case, if the voltage potential is homogeneous on the y direction and the z direction, which means the derivative of v with respect to y equals to 0 and the derivative of v with respect to z equals to 0, then the problem is reduced to a one-dimensional problem. That is, the potential V only varies with x in the x direction. So you have del to the square of V over del of x to the square equals to the minus of rho divided by permittivity epsilon. Okay, there is a reason why we introduced equation 5.55. We will see that later in the example of this section. Now we proceed for the discussion of Laplacian equation. If the charge density in a region is 0, which means there is no charge at that point, then the Laplacian of that point, then the Laplacian of the voltage at that point is 0 as well. Can I say that the voltage at that point is 0? No. Okay. Laplacian is the variation, spatial variation of voltage in the neighborhood of that point. So you need to look into its neighborhood to find out if it has a 0 Laplacian. Okay. So it doesn't imply that zero charge density doesn't imply zero potential. Okay, be careful about that. So we can use the Poisson equation to check, to examine if there is a charge at your interested point. Okay, just perform second order, just perform Laplacian operation on it, or second order derivative in terms of x and y and z direction. And Laplacian equation also satisfied by the potential in conductor under the steady state condition. Okay, so in the next few slides, we will look into this problem. It's just a simple concept. So let me let's review it a little bit, preview it a little bit. So if there is a steady current in the space, will that build up magnetic field? 只要空间中有一个 DC 电流的话，它会不会产生磁场？会。它会不会产生电场？ Will it build electrical field? Nope. Okay. In the case of a steady state, in the DC condition, electrical field comes from electrical charge, non-moving electrical charge. And magnetic field comes from currents, even though you know that it's composed of moving charge. But anyway, they can be regarded as different source. They are not the same. Okay. So current in the DC state, which is made of moving charges, should be can be regarded as a different kind of source, the source for producing magnetic field. So if we look into in the next few graphs, we will try to understand why DC current does not produce electrical field. So for the steady current condition, that is, the time derivative of low equals to 0, then the continuity equation, which specifies the relationship between divergence of J and time derivative of low, must equal to, which equals to 0, the plus of the 2 equals to 0, and we know the time derivative of low equals to 0 as well. Then the divergence of J, which is DC current, equals to 0 as well. And what we're gonna do is replace J with sigma times E. Sigma is what? 来上这门课都是自愿的嘛，对不对？没有人逼着你们修电磁波嘛，对不对？在现在的 condition 的现在的8选3的状况底下，所以这个关系还记得吗？西格是什么？西格玛是什么？电导电系数OK。So in a conductor, if you apply a voltage difference, no, not voltage. Yeah, voltage difference is easier to say. Okay, if you apply electrical field onto a conductor, then you will move the free charges to form the so-called current. So the current density is proportional to the amount of electrical field intensity as well as the conductivity. So J equals to sigma times E. And we can further identify E as the negative of the gradient of V. So you have minus sigma gradient of V. And what? Okay, so we apply this relationship to equation 5.63. So JC is replaced with sigma E, and sigma is strong to the outside, is moved to the outside, so you have divergence of E, which can be further replaced with minus of gradient of V. Then you should identify, you should be able to recognize this relationship by now. That is, the divergence of the gradient of a scalar is the Laplacian of the scalar. 好，这定义哦，这个是定义哦，啊，所以任意的存量的梯度的散度就是它的 Laplacian。Okay, so we can modify it as the minus sigma times the Laplacian of voltage, electrical voltage potential V, and it equals to 0. So for electrical for electrical current J, even though you have electrical current density on that point, the Laplacian of the voltage, electrical voltage, the electrical potential at that point still goes to 0. So DC current and steady charge can be regarded as different source. They are not the same. They don't have the same behavior. Okay, so next we will try to introduce the application for Laplacian equation. It can be used to find the potential distribution in a region between two conductors, giving the charge distribution on the surface of the conductors or the potential of the conductors, or a combination of the two. This procedure involves solving Laplacian equations subject to the boundary condition on the surface of conductors. So what is the boundary condition on the surface of conductor? 拄则还咧困的哦，即摆莫困啊哦，因为等下有一题就甲这有关系。So what is 听到我在 murmuring 嘛？ So what is boundary condition on the conducting surface? So suppose you have a perfect electrical conductor, where you have normal electrical field. Or can you have tangential electrical field? 哪一个可以有，哪一个不可以有？ you don't have tangential electrical field on a conductor surface. You can have normal component of electrical field intensity on a conducting surface, which appears with electrical charge. As long as you have electrical charge on the conducting surface, you can have normal component for electrical field intensity. And the other two boundary conditions are associated with normal component of magnetic field intensity and tangential component of magnetic field intensity. Which one must go to 0? Which one can be non-zero? 猜一下。对称性猜嘛，对不对？所以这个不可以有，这个可以有，So you are allowed to have a tangential magnetic field on a conducting surface, which come with what? 猜一下，这是 electrical charge， 这个嘞 ，electrical current J 哈 ，OK。我把它画成圈圈的话，意思是因为那个电流是，我忘记怎么，我不知道是朝内还是朝外了，反正是跟你那个 HT 的方向是正交的，可以吗？好，所以这个是电流 J 啊，好，都有看到了哈， So of course we will apply the boundary condition to solve this kind of problem. Okay, so now let's look into example 5.6, which comprise two infinite plane parallel perfect conducting plates occupying by two planes. One is located at x equal to 0 and the other is on x equals to d. And what we know about it is the voltage potential on the lower plate, that is x equal to 0, the voltage potential here is referred as 0. And at x equals to d, the voltage potential is V sub 0. This is actually a quite useful scenario, quite realistic scenario. And you may wondering or question my statement. Well, we don't have infinite plane, right, in real life. Okay, but think about parallel plate capacitors. You compress two planar conducting surfaces, and the distance that separate the two planes is very, very small. So locally, suppose that you are a small ant, but you must be smaller than ant, okay? small coronavirus, all right, okay? So if you are a small coronavirus trapped in the capacitor, okay, you will see the parallel, the conducting surface on top of you and below you are extending infinitely on the horizontal plane. Okay, so for capacitors, parallel capacitor, this is a pretty realistic assumption. So it has it's the field. So here you can see the dashed line are what? Equal potential surfaces. The solid area are electrical field pointing from high potential to low potential, which is in contrary to the definition of gradient. Okay? So the direction of electrical field is the negative of the gradient of V. And it has no dependence on y and z direction. We have an infinite parallel plane. So are you happy with this electrical field intensity direction? Well, I don't know I'm happy or not, but I know it's satisfied the boundary condition, right? You have normal component of electrical field intensity. The E field direction is normal to the conducting plate, right? So the boundary condition is satisfied. And what comes with this boundary condition? Electrical charge, okay? So here we have electrical field intensity pointing from here downward. So we have positive electrical charge on top plate. And here we have electrical field intensity point into the lower plate. So we have negative electrical charge on the bottom surface, all right? So the boundary condition should be satisfied with this result, which we have not derived it yet. Okay, so let me show you how to derive this. So here is the Laplacian equation we need to use because this is a one-dimensional problem. The parallel plate extends to infinity in the y and z directions. So it is a one-dimensional problem. You only have the spatial variance in the spatial variation in the x direction. So you have del square of V divided by del x to the square must equal to 0. Why we put 0 on the right hand side? Why do we put 0 on the right hand side? Because in the parallel plate, there is no electrical charge between the two plates. So for parallel plate capacitor, you're supposed to place a layer of insulator in between, 对不对？你应该在中间放一个绝缘体的，所以在中间里头不会有自由的电荷，不会有电荷、正电荷或负电荷，所以那边的 charge density, the charge density within the capacitor is 0. So equation 5.64 are something you can find from your engineering mathematics textbook. That is the general solution for one-dimensional second-order differential equation. It should be in the form of ax plus b. Okay? Which is the result of performed integration of x twice along the x direction. So now we can apply, so 5.64 is the general solution to satisfy the second order differential equation in a one-dimensional problem in rectangular coordinate system. It will be a different story if we are looking in the cylindrical coordinate system or spherical coordinate system. The general solution will look differently. But for rectangular coordinate system, it's in the form of ax plus b. So the unknown that we need to solve are a and b. What can be used to help us to solve a and b? Use boundary condition. We know that v at the position of x equal to 0 equal to 0. And we know the voltage at the position of x equal to d equals to v sub 0. Okay, so 0 voltage and v sub 0 voltage are the two boundary conditions we have. So we substitute x and v into this ax plus b equation, and we found out b equals to 0, the constant b equals to 0, and the constant a equals to v sub 0 divided by d, which is the distance between the two plates. Can you solve this problem for me? Okay, I suppose you. 为什么？我也怎么就英文上的想到我小时候看我女儿上那个 Dora 的那个 Explorer， 不要把各位当成小狐狸还是 Dora，OK 好，没问题啊，很简单的。Okay, so that's a relatively simple problem. Okay, so substitute A and B, that is, which are derived from the boundary condition. We end up with a specific solution. Okay, ax plus b is the general solution. Now we have equation 5.65. This is the specific solution, which is derived by taking into account of the boundary condition. So the voltage V equals to V sub 0 divided by D times the x coordinate, x, okay? And note that this is only valid between x, for x greater than 0 and x smaller than D. What is the voltage beyond 0 and D? What is the voltage outside of the capacitor? Well, actually, in chapter 1, we have already seen the electrical field intensity built up by an infinite plane of electrical charge, right? What is that? If I have positive charge here, it will build up an E field in this direction on the top and in this direction on the bottom, right? And it extends to the infinity. It extends everywhere. Mathematically, you can interpret the problem like this. You have another surface made of negative charge. Then the field built up by this negative charge goes this way. So if however, if the charge density on the top plate and the bottom plate are the same, the electrical field built by the two plates will cancel on the top and cancel in the bottom, upper region and the lower region. So you can only have field pointing this way, a homogeneous field distribution pointing from top to bottom between the plate, okay, and nothing out there. So this can provide a satisfying mathematical interpretation. Oh. But are you satisfied with this interpretation? Well, physically, you can think of the energy. The energy is locked up within the two plates. Okay, so you won't feel a thing above or below the capacitor. So you may think of, if you try to interpret this in terms of physics, you may think of this problem in terms of energy, okay? And you can also find out the relationship between voltage and electrical field intensity. So taking the gradient of V and taking the negative sign, you end up with the electrical field intensity expression. What is the implication of the minus sign here? It's pointing downward, okay? The E field is pointing downward. And you can find out the electrical charge density on the top plate and bottom plate using the integral form of Gaussian's law of electrical field. So you are taking the surface integral on the top plate, you end up with a positive electrical charge density. If you take the closed surface integral on the bottom plate, you end up with a negative electrical charge density. And if you times the electrical charge density with a unit surface, you can get the charge in that space. And let me finish this quickly. If you divide the charge with the voltage difference in this space, you end up the capacitance of this structure. This is actually the per unit area capacitance. Per unit area capacitance. Capacitance is defined as the ratio of charge over voltage difference. Okay? This is not the total capacitance. This is the per unit area capacitance. And here are some relationships you can find for solving this kind of the procedure that you may need to solve this kind of problem. All right, so let me stop